topic vector subspaces. This topic is prescribed in the syllabus of Paper 1 Linear Algebra of the class BA BSc BA B.Ed Sem 6th of Guru Nanak Dev University. Firstly, I have taken the definition of vector subspace. A non-empty subset W of a vector space V over a field F is called a subspace of V if W itself is a vector space over the same field F under the binary compositions defined on V. So by these properties we can say that W is closed under vector addition and scalar multiplication. Here I have taken two examples of vector subspaces. Firstly, I have taken an example of a set W where W is the set of all the points x0 where x belongs to R, or you can say that W is the set of all points on the x-axis. Here W is a subspace of vector space R square where R square is the set of all points in the coordinate planes, or you can say R square is a set of all points xy where x and y both belong to R. Second example I have taken from the vector space R cube. R cube is the set of all triplets ABC where A, B and C belong to R. So we have taken a subset of R cube W where W is the set of all points 0 BC where BC belong to R, or you can say W is the set of all points in the coordinate in the YZ plane. Next let's do one theorem on vector subspaces. This theorem gives the necessary and sufficient condition for a non-empty subset to be a vector subspace. This theorem says the necessary and sufficient condition for a non-empty subset W of a vector space VF to be a subspace of V is that alpha x plus beta y belongs to W for every alpha beta belong to F and xy belong to W. Let's do its proof. So firstly we will take the necessary condition of this theorem. In the necessary condition we will take W as a subspace of VF. So let's W be a subspace of VF and we will prove the condition. That condition is alpha x plus beta y belongs to W for every alpha beta belong to F and xy belong to W. Now since W is a subspace of VF and we had already done that if W is a subspace of VF, it is closed under vector addition and scalar multiplication. So therefore whenever alpha belongs to F and x belongs to W implies alpha x belongs to W, and beta belongs to F, y belongs to W implies beta y belongs to W. These two properties come from the scalar multiplication property of W. Next, whenever alpha x belongs to W and beta y belongs to W, that will imply alpha x plus beta y belongs to W. So this property comes from the vector addition property of W. So from these two conditions we will get alpha x plus beta y belongs to W for every alpha beta belong to F and xy belong to W. This covers the necessary condition of this theorem. Next is the sufficient condition of this theorem. In the sufficient condition we will take alpha x plus beta y belongs to W for every alpha beta belong to F and xy belong to W, and we will prove that W is a subspace of V. So to prove W is a subspace of V, we will prove that W is closed under vector addition and scalar multiplication. So firstly we will show that W is closed under scalar vector addition. So for that we will put alpha is equal to 1 and beta is equal to -1 in the given condition. So we will get, you can see here, that is whenever alpha is 1 and beta is -1, we will get 1 into x plus minus 1 into y belongs to W. So that is x minus y belongs to W. So this gives a W is closed under vector addition. The next part is to prove that W is closed under scalar multiplication. So for this purpose, we will substitute beta is equal to 0 in 1. So we will get alpha x plus 0y belongs to W. From the previous slide, we can see that alpha x plus beta y belongs to W. So whenever we substitute beta is equal to 0, it will become alpha x plus 0y. So that is alpha x plus 0y belongs to W. That implies alpha x plus 0 belongs to W, or that implies alpha x belongs to W. And this gives the scalar multiplication property of W. So that is W is closed under scalar multiplication. So by these two properties, that is x minus y belongs to W for every xy belongs to W, and alpha x belongs to W for every alpha belongs to F and x belongs to W, we get W is closed under vector addition and scalar multiplication. So therefore, we can say that W is a subspace of VF by the definition of subspace of a vector space. Hence the theorem is proved. Thank you.